So I will start with these presentations with a talk about the hemispherical properties of the inner core, and I will propose a growing mechanism which may explain this property. Okay, so I will first recall some general properties of the core, but probably all of you know something about that. And then I will describe this model which may explain this hemispherical property of the inner core. And this model implies a crystallization, translation, and fusion of the inner core. And then I will discuss some consequences and difficulties of this model and then conclude. Okay, first I recall these features concerning the core. So I start from outside. You have the mantle, which is basically made of rocks. At the base of the mantle, you have the D double prime layer, which is very heterogeneous. It's often considered as the place where the subducted plates are recycled, so it's very heterogeneous. Then you have the core mantle boundary, CMB, which is it's a very strong discontinuity, and it is sharp. It's a first-order discontinuity, and it has a low topography. Then you come in the liquid core. For seismologists, liquid core is a medium which is very transparent. It's a real liquid, I mean as liquid as the water, so that no S-wave may propagate inside. And it has a very low attenuation, so waves go through the liquid core very easily. At the base of the liquid core is a layer which has a low velocity gradient from the point of view of seismic waves, and it is considered as a high density layer. And then we come to the inner core boundary. Again, it is a first order discontinuity, but not as sharp as the core mantle boundary. I mean, at least the velocity contrast is not very strong. Then we come inside the inner core. The outermost inner core is made of an isotropic layer of iron. And then we come inside the domain of anisotropy. The properties of this anisotropy are still debated, but it is generally accepted that more or less the high velocities and strong attenuation are parallel to Earth's rotation axis. And then at the center of the inner core is what we call the innermost inner core, where it is, well, at least we know that the anisotropy is different from the rest of the inner core. The liquid core is made of iron with light elements inside, so it's a liquid alloy of iron, and the inner core is also an alloy of iron, but it is solid and it is depleted in light elements compared to the liquid core. Also, some scientists believe or have demonstrated that there is possibly a differential rotation of the inner core with respect to the mantle, but again, this is debated. And finally, but this is not an information of seismology, it's an information of thermodynamics, the inner core is young, probably less than 1 gigayear, or say about 1 to 1.5 gigayears, and its radius is increasing slowly at a rate of about 0.5 millimeter per year. Okay, another property which is important because it will be the basis of what will follow is the fact that there is a hemispherical heterogeneity in the inner core. And this is not trivial. I mean, everybody may think that the inner core has a symmetry with respect to Earth's rotation axis, and this is not the case. This asymmetry is seen in the domain of anisotropy, which is studied thanks to the differential travel times and amplification of these two waves, PK-PDF, which has its turning point in the solid in the inner core, and PK-PBC, which is a reference phase because it has its turning point in the liquid core, which, as I told you, is homogeneous. So, as you may see here, the Western Hemisphere is fast, with short travel times, and the Eastern Hemisphere is slow for this path parallel to Earth's rotation axis. So this, well, it's the opposite for paths which are parallel to equatorial plane. So this hemisphere is more anisotropic than this one. Now, if we look at the isotropic layer, it's studied thanks to the differential travel times and amplitudes of, again, this PK-PDF phase, which turn inside the inner core, and this PK little I KP reflected phase at the top of the inner core. These two phases you may see here. And here you see that the Eastern Hemisphere is fast, and the Western Hemisphere is slow. This figure will, we will come back to this figure later, in trying to add more data in the high latitudes, because as you see here, there are not so many data close to the poles. The Eastern Hemisphere is also an hemisphere with high attenuation, and the Western Hemisphere with low attenuation. So, to summarize, it's what I just showed here before. The difference between the Western and Eastern Hemisphere for the uppermost isotropic layer and for the anisotropic structure. And the question is now how to explain that. In fact, there are two possible models up to now. The first one, I will not speak too much about it, is to invoke the thermal heterogeneities at the base of the mantle, at the level of the double prime layer. These heterogeneities will influence the flow inside the liquid core, and this flow, in turn, will generate thermal heterogeneities at the top of the inner core. And this difference of flow at the top of the inner core will induce different textures on the two hemispheres of the inner core. I will mostly speak about this second model, which imply some modes of convection inside the inner core. Okay, I come back to this structure in the innermost inner core, so you recognize the same figure as before for studying this isotropic layer. And now I have tried to add some paths, to have more paths close, which have the turning point close to the poles. We have here the epicenter, station, and turning points inside the uppermost inner core, and the results are here. Again, you may see this Western Hemisphere with blue dots, which are located at turning points of the rays, which are slow. Eastern Hemisphere with the red dots, which is fast. And what is new? Polar regions here appears in green, which means intermediate values. Also, this transition between Eastern and Western Hemisphere is in green, so intermediate values. So it's really clear here, where I have plotted the residuals. It means you can convert that in velocity, in seismic velocities, as a function of distance. You clearly see the dots, blue dots corresponding to the Western Hemisphere, red dots to the Eastern Hemisphere, and in between, polar regions. This can be represented very simply by spherical harmonic expansion, the first degree of spherical harmonic expansions, degree 1, fits rather well this pattern. So it's very simple. Just it gives a particular role to 2 points. Point G here, which is the center of this slow region, and the point on the antipodes, M, which is the center of this fast region. If now you plot the travel times anomaly, so again it's equivalent to seismic velocities, as a function of the distance to point G, you see here low velocities in G, high velocities in M, with a continuum between the 2 points. So when you go from G to M, the velocity increase. In the same way, you may show that the attenuation is low in G and stronger in M. This is this tendency, which is not as clear, but which really exists. So to summarize, we have now something which is quantitative in G and M, with P velocity and attenuation or quality factor in G, P velocity and quality factor in M. You see, it's really different values. And in between, these values have a continuum. They have a linear trend. So this information is important for 2 reasons. The first one, because we have values that we can interpret, and also because we have something which is opposite to what is observed in the mantle. In the mantle, when you have high velocities, you have low attenuation. And this can be explained by thermal anomalies. Here you have the opposite. You have, at the same time, low velocities and low attenuation. So it cannot be explained by thermal anomalies. And what is suggested is that it is due to scattering by the grains of iron in the inner core. So it's this model we will check. From these values, we will try to determine the size of the grains of iron which produce scattering. How to do that? I just give here the principle. You have an incoming wave which goes through a medium which is able to scatter the waves. You have energy which is scattered everywhere in all the directions. And at the output, you have a wave which is delayed and attenuated with respect to the incoming wave. And the way this wave is delayed and attenuated gives information on the medium. It's what we will do for the inner core. We have this ray with PKP ray which go inside the isotropic part on the inner core, and we consider this box here. This box is in fact a patch of grains. Each of these grains is anisotropic. It's characterized by size and also by some properties linked to the anisotropy. But these grains have all the possible orientations, so that at the macroscopic scale, this medium is homogeneous and isotropic. But each boundary is able to scatter the wave because the properties are discontinuous at the boundaries. So the medium is characterized by the form of iron, which we have considered cubic or hexagonal iron, by the elastic constant which describes the anisotropy, and by the size of the grains. We have considered, in this figure, you have considered the hexagonal iron, but in fact we have also made the computations for cubic iron, and the results are very close to each other. So in fact, we cannot discriminate between these 2 forms of iron. So I show the results for HCP iron. We have these values which were given by the previous analysis from VP and QP. And if we plot the P velocity, VP and QP, and well, here I give the results of many simulations, and the statistical, say all the results we have obtained are here. Here is the grain size, and you see that to explain the values in G, we must have grain size, say in this blue-green region, so about 500 meters, and to explain the QP and VP values for the M region, we are in the red domain, so we are somewhere here. So it's grain size of about 10 kilometers. It's big grains, very big grains of iron inside the inner core. This makes a grain size ratio which is between 7 and 50. So you imagine it's very big grains in the inner core, but you may remember that the gravity is very low, so grains have the possibility to grow, and also the conditions are very different from what we have at the surface of the Earth. Okay, how to explain that? Well, I come back to the previous one. So we have small grains here, big grains here, and intermediate values here. I mean small for the inner core, okay? So we know that the grains are able to grow just because of time, say. When you have small grains, they slowly have a tendency to have a coalescence of their boundaries. Says there is a migration of the boundaries to come to big grains. This is because you have this principle of minimum energy, so there is a tendency to decrease the energy at the grain boundaries, which is minimum when the grains grow. So here you have this growth of the grains by migration of the boundaries, as I told. Small grains are here, big grains are here. So there is, so the grains will have their crystallization here, because they will preferentially crystallize to this form, and then with time become larger. So this increase of grain size from west to east implies that this side here is older than this side. So it's logical to imagine that there will be an edging of the grains of the inner core from G to M. This is possible in convection models. Usually when you consider convection in the inner core, you just imagine that the inner core is a kind of box, spherical box, which is closed, and inside this box you are looking at convection. In fact, there is no reason to close the box, because the inner core can melt and can freeze and can have exchanges with the outer core. So if you open the boundaries, the solution of convection are completely different. In particular, the most trivial solution of the equation of convection are a constant velocity inside the inner core, which in fact constant velocity means translation. So the simple mode of convection is a translation of the inner core with crystallization in one side, melting at the other side. I may explain that in a very simple way, probably not as well, it's just to that you could understand what occurs. Imagine you have freezing on side G. This will load this side because iron is more heavy than liquid. This will displace the center of mass on this side. This is new center of mass. But the center of mass must be along the rotation axis. So there will be a translation so that the new center of mass become again on the rotation axis. But this will shift the boundary here to this new dashed boundary. And this part here will be exposed to temperature and pressure conditions where freezing will occur. So this will freeze. But this freezing will again displace the center of mass here. And again, a translation will be necessary to put the center of mass on this axis. But this will expose this part of the inner core to pressure and temperature condition where freezing will occur. So freezing will occur again. And this again will push the inner core. So we will have this permanent motion where we have a translation of the permanent translation of the inner core with freezing on this side, melting on this side. Of course, the inner core will have no displacement because it will always be very, very small, so that the inner core remains as this place where it has a center of mass here, but permanently this will freeze and this will melt. The consequence is that we have the edge inside the inner core, which will increase from west to east according to these curves here. Here is the young inner core, is the oldest inner core. This age variation will depend on two factors. Of course, the translation velocity, and also the time at which this process began. Here are different configurations. Well, I just give, there's in fact 3 cartoons. The first one corresponds to a translation velocity which is equal to the crystallization velocity, so 0.5 millimeter per year, about. The second is translation velocity, which is 3 times the crystallization velocity, and the last one, 10 times. In each cartoon, the top gives the age, and the bottom gives the grain size. On the left is a translation since 1 gigayear. It means more or less since the beginning of the formation of the inner core. On the right, it's since 200 million years. So what we see? If we started the process very early and at a low velocity, we still have inside the inner core some primitive inner core, here in red, which has been pushed close to the boundary, but it's still present. If the process started later, this primitive inner core is almost not really centered in the inner core, but it's still inside the inner core. By contrast, if we looked at fast translation, here, for example, we have completely lost the original inner core. Everything has disappeared. We have completely lost the memory of the history of the inner core. It's a little bit like, plate tectonics. When you look at the ocean floor in plate tectonics, after 180 million years, you have completely lost the history of the plate. Here it's more or less the same. You just have young material, but the inner core is older than its material. Okay, and you have, of course, intermediate possibilities depending on these 2 parameters, velocity and time of beginning. On this figure here on the right is plotted the grain size ratio as a function of translation velocity and time of beginning of the process. So here, 1 gigayear, 200 million years. I said before that the grain size ratio is between 7 and 50. 7 corresponds to this yellow domain here. So all what is on the right, yellow in red, could be accepted. So it means that if you look at the value here, you must have a translation velocity of at least 3 times the crystallization velocity. But of course, if you look at higher values, you can be in this domain here and have translation velocities which are much, much higher, say 20, 50, really high values. But the minimum is 3. So this model has a lot of consequences. I will not go through all these consequences, but just look at a few things and pay more attention to point 5 and 6. So I go quickly through the first one. 10 minutes? 5 minutes? Okay. So first, we have observed that we have still this dichotomy between the two hemispheres. It means that this process is still active today. So it means that convection is still active today, and for this implies that the inner core must be young, because it must be in superadiabatic conditions. The second question is, why is the translation in the equatorial plane? And here there are many reasons. The first reason is that heat is preferentially extracted at the equator, in particular because of the form of the flow inside the liquid core, which evacuates the heat more easily at the equator. But also there is probably an influence of the inner core flattening due to Earth's rotation. Well, this process is hardly compatible with inner core differential rotation because it's clear that the two hemispheres have been constant since, say, at least 200 million years. So if the rotation of the inner core was fast, it would have been completely destroyed, this pattern. So how to maintain the innermost inner core at the center of the Earth? This is a problem. This is not a problem if the innermost inner core just corresponds to a phase transition, to a phase change of iron related to pressure and temperature conditions. So I go now to point 5, how to explain the dense layer at the base of the liquid core. This is some work of my colleagues from Lyon, which have also proposed the same model. This layer at the base of the liquid core is well documented. So when you freeze here the iron with light elements, we'll have a tendency to release light elements so that the inner core will be depleted in light elements. When you melt here, the melting is, of course, also depleted in light elements. So it will enrich the base of the liquid core in depleted material. This depleted material will again freeze, again release light elements. So the inner core will be more and more enriched in pure iron, and when it melts, it will of course give also a layer which is more and more enriched in pure iron, so denser. How to explain the anisotropy? Here it's necessary to invoke some higher degrees in convection. Here it's what we were looking at with convection, which is in fact simply a translation of the inner core. If we look at much lower viscosities, we have a kind of convection as if we were in a box with closed boundaries, and in between we have this regime where one hemisphere has a complex convection and the other hemisphere has a pattern close to translation. So we are able to generate a hemisphere where there is anisotropy and the other one where the anisotropy is low. And this gives a constraint on the viscosity, which must be close to 10 power 18 Pascal second. Well, maybe I will. Well, I have tried to check this pattern with seismological data, again this kind of data here. This data must be very scattered on this hemisphere due to the complex pattern, and they must be more simple here due to this very simple pattern. That's what I look here. The standard deviations of the residuals are in fact different on the two hemispheres, but this difference is not as big as I would expect. So clearly this model must be refined. Okay, now I come to the conclusions. We have seen from the seismic observations that there is an evolution of seismic velocities in attenuation in the isotropic layer from G to M, which is explained by an increase in iron grain size from west to east. This can be explained by a permanent translation from west to east with crystallization on one side and melting on the other side. So it means that the inner core grows from its western side, that the edge increases from west to east, but that the inner core may look younger than it is in fact really. The translation velocity must be at least 3 times the crystallization rate, but my colleagues in Lyon found, on the basis of the explanation of the dense layers, they found a velocity which is at least 20, so this could be debate. This, as I told you, they explain the dense layer at the base of the liquid core with this mechanism. And we can explain the hemispherical variation in the isotropic layer with this model, but if we invoke also higher degrees of convection, it is possible to also explain the anisotropy. Okay, I guess in the future, this model will have also to include the thermal forcing by the mantle. So, as you see, it has a preliminary view of the inner core. So, my conclusion is this plot from that Jules Verne, more than 100 years ago, had anticipated that the GM axis was a really important axis. So, it's in French. Science is made of errors, but these errors are useful because they lead slowly and slowly to what is true. Thank you.